Good morning. I, Professor P.S. Lokre, on the behalf of Dr. Ashok Guzar Technical Institutes, Dr. Daulatrao Ahir College of Engineering, Karad. Welcome to the Day 3, Session 5 of ATAL FDP on Industry Academia Synergy in Disaster Management and Resilient Infrastructure for Advancing Sustainable Development. It gives me an immense pleasure to introduce today's distinguished speaker, Professor P.K. Deshpande, an experienced geologist, academician, researcher, and an eminent resource person in the field of geology and geoinformatics. Professor P.K. Deshpande has over 32 years of rich teaching, research, and consultancy experience. He is presently working as an associate professor of geology at Walchand College of Engineering, Sangli, one of the premier institutes in the region. He holds an MSc in geology from the University of Pune and also MA in English from Shivaji University, Kolhapur, reflecting his strong academic foundation and excellent communication skills. Throughout his career, he has served reputed institutes such as Rajaram Bapu Institute of Technology, Government College of Engineering Karad, Sardar Patel College of Engineering Mumbai, and Walchand College of Engineering Sangli. Professor Deshpande has undergone advanced training in geoinformatics from IIRS Dehradun and JNTU Hyderabad. His research interests include landslide hazard zonation, flood hazard mapping, watershed management, engineering geology, and post-disaster rehabilitation, which are highly relevant in today's context of climate variability and disaster risk reduction. He has published and presented more than 35 research papers in national and international journals and conferences. He has delivered numerous expert lectures on remote sensing, GIS, seismology, plate tectonics, and seismicity of Maharashtra, and has organized several workshops and STDPs on remote sensing and GIS applications. He has also played a vital role in establishing the remote sensing and GIS cell at Walchand College of Engineering through AICTE model of schemes and has provided consultancy to various government and private organizations. With his vast academic experience, we are extremely fortunate to have PK Deshpande with us today under this Atal FDP. I request everyone to warmly welcome Professor PK Deshpande, and we look forward to an insightful and enriching session. Thank you. Over to you, sir.
Thank you so much, sir. Just in my introduction, there was a smallish mistake that I am now retired. I got retirement before 2 years from Walchand College of Engineering, Sangli, and now I'm retired associate professor. Let me share the screen, please. Share option. Am I audible? Are you able to see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Are you able to see the screen?
Yes, sir. Screen is visible.
Yes, sir. The screen is visible.
Yes, sir.
Able to see the screen, please? No? Is that? Am I audible?
Sir. Yes, sir, you are audible and your screen is visible. So you can start, sir.
Okay, thank you so much. Thank you so much. Thank you. First of all, I am very thankful to the organizers of this Industry Academy Synergy in Disaster Management and Resilient Infrastructure for Advancing Sustainable Development, ATAL FDP, for giving me the opportunity to speak a little about seismology and aspects of Koyna earthquake related with the disaster management. A little bit late, so we'll start directly with the topic, that is earthquake. So many of us, we have heard the term earthquake. We have experienced the earthquake because we people are living in the Koyna region, just 55 kilometers from Koyna, which is very famous pocket that experiences earthquake every year, and the frequency and magnitude of the earthquake is considerable. Let us see first the definition of earthquake. What is the earthquake? Many people have defined earthquake in many ways. So some people say that vibration of the earth's surface by shock waves that are generally usually generated by energy released from the rocks rupturing under the stresses. Many people have defined sudden motion of trembling in the earth caused by and so and so. In many ways, the earthquake is defined. But for the civil engineer, a very simple definition of the earthquake is shaking of the earth, because he has to consider that particular factor while designing the civil engineering structure. So simple definition of the earthquake is shaking of the earth. This Charles Richter is the father of seismology. Just I am showing, just let us recall him before going in for learning the basics of seismology. This is Charles Richter. Now let us see what are the different types of earthquake. So for the civil engineering, we should know the while designing the structure, the types of earthquake are very important because especially the depth of focus depends on this type. The first is dynamic type of earthquake. So whenever we are standing on the railway platform whenever the train passes, the passengers standing on the railway platform, they experiences the vibrations. Whenever there is a blasting in the quarry somewhere, then the surrounding villages may experience the vibrations. Nearby village may experience vibrations. So, because of the passing lorries, uh, the roadside houses, they experience vibrations. So all these vibrations, because of this smallish dynamism, you say they are known as the dynamic type of earthquake. In case of dynamic, even a person walks on the ground, a little vibrations are there, the ground vibrations around him. They are also the earthquake, and they are treated as dynamic type of earthquake. Because of the somewhere in the workshops or in industry, the machinery is being operated, drill machine is there, lathe machine is there. So these vibrations, they are also treated as earthquake, because for civil engineer, yes, they are earthquakes. So they are dynamic type of earthquakes. In case of dynamic type of earthquakes, the focus is almost near the epicenter, that is almost on the surface. So very, very, very shallow focus. They have very low intensities, low magnitudes, and very less felt areas. So they are the dynamic type of earthquake. The second type of earthquake is volcanic type of earthquakes. So just before the volcanic eruption, or during the volcanic eruption, the surrounding villages of the volcano, volcano is a vent or opening through which the molten rock material, that is magma or lava, is erupted out on the surface. Such type of conical hills, we can speculate they are the volcanoes. So whenever the lava erupts out or before just eruption of volcano, the surrounding villages experience the vibrations. These are known as volcanic type of earthquake. Again, these volcanic type of earthquake are shallow focus earthquake, and they are again of lower magnitudes as compared to the higher magnitudes as compared to dynamic type of earthquake, and their intensities may be considerable, but they are limited to the villages surrounding the volcano, nearby the volcano. They are volcanic, so you may say that failed areas again little low volcanic type of earthquake. They are associated with volcanism. They are associated with the magmatic activities. So they are volcanic type of earthquake. Then what are the tectonic type of earthquake? Now listen carefully the sentence that I am saying. What is tectonic? Geotectonics means what? When the large rock masses are subjected to pressures. See, when large rock masses are subjected to pressures or strains over a period of time, and suddenly they rupture. Suddenly they rupture, producing a fault. And during the fault movement, the seismic waves are propagated in all directions. They reach to the surface of the earth, and the earthquake is experienced. So these type of earthquakes which are related to geotectonic activities, the earthquakes which are related with the fault movements. See, fault is nothing but it is a fracture in the rocks. Fault is a fracture along which there is a relative displacement of the rock masses on either sides have occurred. They are known as a fault. And during the large fault movements, whatever the vibrations which are experienced, they are termed as tectonic type of earthquakes. Yes, normally when you use the term earthquake, Koyna earthquake, Kilari earthquake, Bhuj earthquake, Karakoram earthquake, so earthquake occurring in the Himalayan regions, these are all tectonic type of earthquake. They have the depth of focus may vary. They may be shallow focus, they may be deep focus. Focus of the depth of focus may vary. They have very large, extreme, several thousands of square kilometer felt area is there. Their magnitudes are high. Their intensities are very high. They may be destructive. They may be disaster. They may be catastrophic. So such type of earthquakes, they are known as the tectonic type of earthquakes. So depending on this, the three types of earthquakes we have seen: dynamic earthquake, volcanic earthquake, and tectonic type of earthquakes. Let us go further. So the term tectonic will be more clear as we go further. So tectonic is, I mean, related to the geotectonics. Geotectonics is the subject which deals with the study of the earth crust and the interior of the earth. That is all geotectonics. The folding, faulting, orogenesis, mountain building activities. These are all tectonic movements which are happening in the earth crust, or the earthquake related with these tectonic movements, or say geotectonic movements, are the tectonic type of earthquake. Again, depending on the depth of focus, the earthquake can be classified as shallow focus earthquakes, intermediate focus earthquake, and deep focus earthquake. If the depth of focus is just up to 60 kilometer, see, focus is a point or place from where the seismic waves are originated. That is the focus of the earthquake. If the focus of the earthquake is just up to 60 kilometer, then it is known as a shallow focus earthquake. In case of shallow focus earthquake, if the magnitude is considerable, naturally the degree of destruction is more because it is shallow focus. The intensity of the surface are extremely high. So if the depth of focus is up to 60 kilometer, if the depth of focus is 60 to 300 kilometers, we say it is intermediate focus earthquake. The fault area is extremely large, but intensities are low in case of intermediate and deep focus earthquake. In case of deep focus earthquake, the focus depth of the focus, of course, from the Earth's surface, the depth of focus is 300 to 700 kilometer. That is deep focus earthquake. See, the radius of the Earth is 6,371 kilometer, and we are classifying the earthquakes depending on depth of focus are up to 700 kilometer. It is because the earthquakes having the depth of focus more than 700 kilometers are not yet recorded. There is no place on the earth where the earthquake having the depth of focus more than 700 kilometers have been recorded so far. So we don't know whether if there are earthquakes below the depth of 700 kilometers, they may not be. Either there are no earthquakes below this depth, or the seismic waves may not be approaching up to the Earth's surface, whatever. So the maximum depth of focus which is recorded so far is 700 kilometers. So that is why the seismicity is shallow focus earthquake, intermediate focus earthquake, and deep focus earthquake. Now let us be introduced regarding some earthquake terminologies. Civil engineers will be especially the civil engineer who is learning the earthquake engineering, who is trying to design the quake resistant structures or dealing with the seismic disaster should know the basics of the earthquake. That is why I'm just entering into the seismology through this particular lecture. So let us see the earthquake terminologies. The place of origin of the earthquake in the interior of the earth is known as the focus. Focus is a point or place from where the seismic waves are originated and propagated in all directions. So that particular is known as a focus of the earthquake. The focus may be a point like, or the focus may be a line like. If the focus is point like, then it is known as focus, say origin or focus or a center of the earthquake. And if it is a line like, then it is known as hypocenter. Hypocenter is a line like. In case of Koyna earthquake, if you see, there may be right from Mahabaleshwar up to Prachitgarh. So this Koyna Varana, there may be a hypocentral line from where the seismic waves are originated. How that I will discuss more a little in the end of the session. Okay, so there may be hypocentral lines, the focus and hypocenter, and the place on the Earth's surface which lies exactly vertically above the center of the earthquake. It is known as, or the focus of the earthquake is known as epicenter. Epicenter is the point exactly vertically above the focus and on the surface of the earth. That is known as epicenter of the earthquake. Try to understand the difference between the focus and the epicenter of the earthquakes. Epicenter is on the surface, focus is vertically below the epicenter at certain depth. The depth may vary. The point on the Earth's surface, diametrically opposite to the epicenter, is called as anticenter. If you join the line of epicenter, focus, then center of the Earth, and if you draw the line, where that line cuts the either side of the globe, that particular point is known as anticenter of the earthquake. The imaginary line which joins the center and the epicenter is called as the seismic vertical. Seismic vertical indicates the shortest distance for the seismic wave to travel up to the Earth's surface. Okay, that is known as the seismic vertical. An imaginary line joining the points of same intensity, equal intensity of the earthquake. See, we'll discuss regarding the intensity of the earthquake later on. Of course, intensity is related with the degree of destruction that is caused with the earthquake, and it is measured with the degree of destruction as well as from the seismograph we can calculate the intensity of the earthquake at a particular location. So the lines, just like the contours we draw the contours by joining the points of equal height, equal elevation, equal altitude. Similarly, the lines joining the points of equal intensity of the earthquake are called as isoseismal lines. And similarly, just like isoseismal lines, the imaginary line which join the points of same arrival time of earthquakes, or the imaginary line which joins the points at which the earthquake waves have arrived at the Earth's surface at same time, they are known as coseismal lines. Okay, try to understand the difference between the isoseismal line and the coseismal lines. And the enormous energy that is released from the focus or the hypocenter of the earthquake at the time of earthquake, and they are transmitted in all direction in the form of waves. These waves are known as seismic waves. Of course, we are going to learn in detail what are the seismic waves and what are different types of seismic waves and their parameters we'll see in the later slides. See here, you can see this is a tectonic, this is a figure of the depicting the tectonic type of earthquake. Here, this is the fault, and somewhere wherever there is a fault movement, okay, from there the seismic waves are originated, they propagate in all direction, causing the earthquakes. And just above the focus, vertically on the surface, there is a epicenter. So this epicenter and focus, these particular terminologies can be cleared from this particular figure. Now let us see what are the causes of earthquake. There is one more type of earthquake, that is intraplate earthquake and interplate earthquake, that I will explain you a little later. Let us see the Now let us see the different causes of earthquake. What are the different causes? Of course, in case of dynamic type of earthquake, it may be volcanic type of earthquake, tectonic type of earthquake. What is the reason for shaking of the ground? The common cause of the earthquake is given, that is the given by the elastic rebound theory. This elastic rebound theory explains uh, how energy is stored in rocks, and after entering in after ending with the elastic modulus, there is a rupture. Okay, and after the rupture, the rocks regain their original position. Rocks bend until the strength of the rock is exceeded because of continuous accumulation of stresses or the strains or say pressure. Rocks are under pressure. See, the earth crust is broken into more or less 20 plates. These plates are moving because of, I'm not entering into the continental drift and plate tectonics, theory of plate tectonics, and all that. But in relation with this causes of earthquake, just I'm explaining this. Because of the earth, these continental plates, because of the plate movements, the energy is accumulated. The plate movements are driven by the convection currents in the upper part of the mantle. They are related with this, all energy is related with all these geotectonic aspects. The energy is accumulated in the rock masses, and because of that, rocks bend until the strength of the rock is exceeded. Okay, and suddenly they rupture. Suddenly they rupture, producing a fault. Okay, and after faulting, they quickly rebound. If you just break, imagine that you are holding a plastic rule. If you try to bend it, it bends naturally, it bends, and until it reaches its modulus of elasticity, okay, it breaks, and again it is quickly rebound to get its original position. Okay, so the similar mechanism happens in rock. This energy is released in waves, and at that time, at the time of rupture, the energy is released in waves. At the time of elastic rebound, the energy is released in the form of seismic waves and radiate outward, propagate in all direction. Okay, and they reach up to the surface of the earth, causing the earthquake. So that elastic rebound theory, it is one of the causes of the earthquake. See, earthquakes are very closely related to faulting, especially the tectonic type of earthquakes. I'm now, henceforth, when I'm using the word earthquake, you remember that I'm talking about tectonic type of earthquake. We'll forget about the dynamic and volcanic type of earthquakes. So, the earthquakes are related with the faulting. This elastic rebound hypothesis, in short, a bed over which stress begins to act, the bed affected by stresses and deformed elastically, then it cracks. Okay, crack is developing at the bend, and along the crack, the two fractured blocks rebound to their original positions, the position of no strain, and as a result, there is a faulting. Faulting means just fracturing the rock and the movement of the rock on rock blocks on the either sides, and the seismicity is developed. So underneath the earth's surface, okay, see, the radius of the earth, as I told you, is 6,371 kilometer, and the crustal thickness is just minimum 8 kilometers in Pacific and maximum 80 kilometers in Himalayas. So average 35 to 50 kilometers is the earth crust. So this particular phenomenon of the earthquake is limited to the earth crust, that is 35 to say 50 kilometer. What we experience this part in these crustal plates or the earth crust, the zeolic and cymatic mass which is associated and which is floating over the upper mantle. Okay, so it is limited phenomenon to a just on the upper part of the earth. So underneath the earth's surface, the beds or mass of rocks are deformed, they are strained, and due to the differential structure, they are subjected to, occasionally they are subjected to tectonic forces causing the earthquake. So fault movement, earthquakes are related to fault. Not necessarily the fault every time should appear on the surface. You may not see the fault lineaments. Lineaments means the line-like structures on the surface. See, in this case, this fault is appearing on the surface, this red colored fault. Am I audible? Are you able to see the figure?
Yes, sir.
Thank you. So these faults, they are appearing on the surface like this. But in case of this particular fault, see, fault is below the ground, within the rock mass which are located at very great depths. They are in the plutons. You can say inside the pluton, this particular faulting is there. So during this particular fault movement, earthquake may happen, but you will not see any lineament or anything, any structural deformation on the surface. So they are the hidden fault. They does not intersect the ground surface. So not necessarily every earthquake, yeah, for every earthquake you may detect the fault. It may not be possible. Of course, this figure unnecessarily appearing in between, it is the one of the effect of earthquake, that is tsunami. Some people say tsunami is the effect of earthquake, or some people say there may be some cause of earthquake which is the same cause of earthquake which is responsible for tsunami, that is responsible for earthquake. There's a controversy, we will not go in that. See, earthquakes are likely to occur at the same place. There is always recurrence of the earthquake. At the first instance of displacement, the broken blocks encounter great friction along the crack, which means only partial structural adjustment take place. Means many times you experience the foreshocks, main earthquake, and the aftershocks. Second thing is that the plate movement is continuous for millions of years. The plates are moving slowly, and the stresses are accumulated. So every time the stresses are accumulated, there is a rupture causing the fault, and there is a tectonic type of earthquake. Again, after some years, for some years stresses may accumulated. Again, there will be earthquake. So this process is being continued. Okay, so there are always recurrence of the earthquake. So seismic zones are developed on the earth crust. Again, when stresses develops, stresses or strain also accumulates, and when it reaches a certain limit, it overcomes the frictional resistance. See, some earthquakes they occur because of accumulation of stresses. At some places, the earthquakes occur because of the strains. Okay, so that is related with the plate boundaries, different types of plate boundaries, which is of course not the part of this discussion. In the plate tectonics, we can where there are strains and where there are stresses, that can be studied in the plate tectonics. See, this is the Indian subcontinent. Indian subcontinent is drifting north 10 degree east. Okay, in this direction, the direction is shown here, this gradually drifting, and because of this particular movement of Indian subcontinent towards north 10 degree east, and it is going below the Himalayas. Okay, from the Himalayan frontal thrust, this particular fault is known as Himalayan frontal thrust, HFT, and from HFT it is subducting below the Tibetan plate, you say. So because of continuous movement of this Indian subcontinent, once upon a time it was in Indian Ocean before 53 million years, 68 to 53 million years before present. And it is drifted for last 53 million years now to get the present location. So I will explain this during the Koyna earthquake. I will explain you more how the stresses are accumulated in the Archean rocks here in Western Maharashtra, and how they are responsible for the Koyna tectonic earthquake, interplate earthquake. That we will discuss a little later on. So this plate movement is the basic cause of this tectonic type of earthquake that I want to say with this particular slide. This is the tectonic map of India. Here you see this Indian continent is moving in north 10 degree east, and see, these are the different faults. These are all thrust fault or the reverse faults. Okay, slightly faults are also associated with them, and the fault movements are being continued, and that is why these, especially the tectonic mountain regions, orogenic mountain regions or epirogenic mountain regions. Orogenic mountains means where the rocks are subjected to folding and they are uplifted to form the mountain chain, like the alpine Himalayan mountain belt. This entire area is seismically active. It is seismic zone 5, you may say. So here the frequency of the earthquake and intensity of the earthquake is considerable. And because of this particular movement of the Indian subcontinent, Indian subcontinent, here is South Gujarat, Western Maharashtra, part of North Karnataka. This entire is the Deccan Volcanic Province. Here we have a 1 kilometer thick um, mass of basaltic rocks, and below the basalts we have the oldest rock, which is known as the Archean gneiss. The Archean gneiss complex or the basement complex is there in this particular zone, and this basement complex, basement rocks or the Archean rocks, they are faulted. These faults are developed, they have been developed because of this motion of the Indian subcontinent. Okay, the plate movement of this in the movement of the Indian plate, and the stresses are continuously accumulated at that particular depth. Near Koyna Nagar, the depth is about encountered about 1 kilometer depth. I will discuss more while talking about the Koyna earthquake, and that is the reason why we are experiencing the intra-plate seismicity here. See, now there are two types of, again, we have seen the types of earthquake, dynamic, volcanic, tectonic type of earthquake. Depending on depth of focus, we have classified the earthquake. Again, depending on this particular location, there are two types of earthquakes. They are plate boundary earthquake and intraplate earthquake. So whatever the seismicity which is experienced in the Karakoram ranges or Uttarakhand or Himachal and Himalayan region, they are all plate boundary earthquake. They are related with the plate boundary. So they are known as interplate earthquake. Okay, and the earthquakes which are happening on the inside the plate, within the plate, they are known as intraplate earthquakes. So maximum say more than 90% of the earthquake in the world, they are interplate earthquake because they are associated with the plate boundaries. Okay, having the considerable magnitude, and they may be shallow focus earthquake. And similar case of this intraplate seismicity and Koyna earthquake, Bhuj earthquake, Killari earthquake, all these earthquake here we are experiencing, even Delhi earthquake, they are the intraplate seismicity because they are related with the stress and strains which are accumulated in the Archean rocks below the sedimentary and igneous formations over them. No earthquake in India is related with any of the reservoir. Koyna Reservoir, Chandoli Reservoir, all even the largest dam in India, that is Tihri, which is 10 times, 11 times more than the Koyna Reservoir. We have Govind Sagar Reservoir in Bhakra Nangal, but they are constructed in these seismic zones. But these reservoirs are not at all responsible for the earthquake that I will discuss later on. Am I audible?
Yes, sir.
Are you able to see this?
Yes, sir.
Yes.
Yes.
Yes, yes. Why the slide is not being changed? Just something went wrong. Just give me a little time. Okay. Problem solved. Yes, no problem. This is the geological map of India. If you observe here, this green color is the Deccan Volcanic Province. This is our area, Deccan Volcanic Province, which is prone to seismicity, especially in the Koyna Varna region. And it is underlain by these Archean gneisses, underlain by Gondwana, underlain by Vindhyans, underlain by Kaladki series of Kadapa system rocks. Somewhere they are underlain by Archean gneisses, somewhere they are underlain by the 2.5 billion year old sedimentary rocks. Okay, and the tectonism in these rocks, older rocks, Archean rocks, 2.5 to 3.5 billion year old rocks, is responsible for the earthquake. This entire trap region, nowhere the traps are faulted. There are no faults, or there is no any considerable structural disturbance in the Deccan trap region. Only if you go to Panvel, Mumbai region, and the traps are just they are tilted. There is a 5-degree tilt, 5-degree dipping towards west. You see, which is known as a Panvel flexure. This flexural bend is there, little in the North Konkan side. Otherwise, this entire Deccan volcanic provinces, the structural disturbance is not there in these basaltic rocks. Whatever structural disturbance which is responsible for earthquake, that lies in the Archean rocks below these basaltic rocks. They are 1 to 1.5 kilometer below the basalts. Now let us be introduced about the seismographs. Seismograph is they are the instruments which detect and record the earthquake. Seismograph is the instrument and seismogram is the outcome. Just like we use the term cardiograph. Cardiograph is the instrument and cardiogram is the output of the graph output of that particular instrument. Similarly, seismograph and seismograms are the terms which are used. So I said seismograph is the instrument that records the seismicity or the earthquake waves. See, the common mechanism of the seismograph, if you observe, of course, there are various types of seismographs. Ancient seismographs were like this. In China, they used they were used to they use this type of seismograph. There is a ball in the mouth of the dragon. Whenever there is a seismicity, so whenever there is a shaking of the ground, these balls they are transferred to frog's mouth. So from that, they used to find out the direction from where the seismicity comes, and they used to do some rituals. This was the very earliest old concept. But nowadays, if you see most of the seismograph, they contain earlier seismograph, of course, they contain heavy weight suspended. I'll show you the figure. So this is the mechanism. So in a hard, compact, massive and intact founding, there is a pillar. It's constructed. This is attached with the horizontal boom with the weight along with this particular tie wire. Okay. And there's a pane or some beam of light. With the help of a mirror, the beam of light is reflected from this particular boom onto the photographic paper, which is wrapped around a rotating drum. And normally, this drum rotates on a pivot so that continuously the shaking of the ground is recorded on this particular photo film. This particular arrangement was there. Whenever there is an earthquake, what happens? Because of the shaking of the ground, the pillar vibrates, and the pillar vibrates, and these vibrations are amplified by this particular horizontal boom, and this graph is recorded on this the film. With this particular mechanism, if you see, you are able to record only the horizontal component of the seismicity, horizontal vibrations, either east-west vibrations or north-south, depending on how you orient this particular instrument. Depending on that, you can record east-west component of seismicity, or you may record the north-south component of the seismicity. The vertical component is not recorded with this particular arrangement. So this is the common arrangement as to the when waves from distant earthquake reach the instrument, the inertia of the weight keeps it stationary while the earth and the support vibrate. The movement of the earth in relation to the stationary weight is recorded on the rotating drum, as I just shown you with this figure. And to record a vertical component of the seismicity, the common arrangement. Of course, these figures nowadays, such type of seismograms are not in use. These figures are just to get the idea. Okay, so there is a vertical spring. There is again strong, hard, compact, massive, intact founding is required, of course, for the seismograph, because the seismicity is recorded from there only. The ground shakes, and the vertical component, because of the vertical vibrations, there is a spring. There's a movement of the spring which is attached with this particular weight, and from the weight, with the help of a beam of light again, the reflected beam of light is taken onto the photographic film wrapped on this drum, rotating on the pivot. The vertical component of the seismicity is recorded with this particular manner. Okay, so in this manner, you are able to record the northwest component, east-west component, and vertical component of the earthquake. Nowadays, seismographs are very, very sensitive. The principle that is used for seismograph is any piezoelectric structure, piezoelectric sorry, not structure, crystal. A piezoelectric crystal is implanted in a very strong foundation. Piezoelectric means crystal means depending on the pressure, its electrical conductivity varies. Okay, and a continuous electric current is passed through this piezoelectric material, and that current is monitored. And whenever there is a shaking of the ground, the pressure on that piezoelectric material varies and the electric current fluctuates. And these fluctuations of electric currents are used to get the seismograph data. So such type of very, very high precision seismographs which are now available, they are available in seismological observatories all over the globe. And they are interconnected now with the help of the satellite. Means when I am sitting in, whenever there is an earthquake, even if there is an earthquake in Alaska, while sitting in Karad, I can take a printout. How the same earth, how that particular earthquake is recorded in Karad, how the earthquake is recorded in Delhi, how the same earthquake in Alaska is recorded in Australia. That data I can get. Even these highly sensitive seismographs, there is a software that can eliminate all the noise because of the dynamic earthquakes or the dynamic seismicity alongside. So people may be walking around, there may be the lorries, there may be blasting in the quarry. All these noise is and only the data which is generated or the vibrations which are generated because of the earthquake, because of the distant earthquake, they are recorded and they can be magnified 75,000 times. Such type of high uh, precision seismographs are nowadays available. Of course, they are working with the same this particular principle. To understand the principle of seismograph, these particular figures are, I think, sufficient with this mechanism. North-south component, east-west component, and vertical components are recorded. In case of Koyna earthquake, the east-west component is very prominent. If you roam around in Karad city or in Koyna Nagar or in Patan or nearby villages in Koyna Nagar, if you observe, the north-south wells, the north-south walls are collapsed. They are buckled, they are collapsed, and east-west walls are standing. Along there may be some inequal on a particular seismic crack. Just observing the crack, you can say yes, it is seismic crack. Seismic crack can easily be identified in this area because of particular east-west vibrations of the earthquake. Whenever if you observe any pendulum or a fan during the earthquake, during the seismicity, it vibrates east-west. So east-west seismicity is prominent in case of Koyna earthquake. I think there is a reason the spin of Earth spin may have a little role in the east-west vibrations. Most of the earthquakes on the globe, the east-west component is very prominent. In Japan, if you go east, along with east-west component, vertical component is prominent because the cases of roof collapse are more in Japan. Okay, and in our area, the collapse of north-south walls, the walls which are aligned north-south, they are collapsed because of the east-west vibrations. Now, civil engineers, while constructing, they should remember this fact also because seismicity, every earthquake in Koyna, जो seismicity that is experienced is east-west. That is very, very important. And we are lucky to have our Koyna Dam. The alignment of Koyna Dam is east-west, not north-south. And because of east-west construction of Koyna Dam, the nature itself has given a sort of a safety. It is a gravity dam. It is constructed on a very strong, compact, massive, intact in situ rock along the dam alignment, as well as along the abutments. Very strong founding conditions are there. And most important is its east-west alignment that has given stability from seismicity. That is very important So we are lucky in that way as far as Koyna Dam is concerned. Now let us see uh, what are the seismic waves. Earthquake vibrations, see, originate from the focus or the hypocenter and are propagated in all directions. These vibrations travel through the rocks in the form of elastic waves. They are known as the seismic waves. Mainly, there are three types of seismic waves. They are called P waves, S waves, and L waves. The focus may be of any type. It may be line-like, hypocenter, or it may be a point-like focus. These three types of waves are certainly propagated: P waves, S waves, and L waves. Every earthquake is associated with three waves. It is not a thing like from some earthquake only P waves are there, from some earthquake S waves are there. Not like that. During the every earthquake, three types of waves are generated. They are propagated in all directions. They reach up to the surface and they cause some degree of destruction. They may cause disaster. Okay, P waves, S waves, and L waves. What are the P waves? P waves are the primary waves. Seriously, they are called as primary waves, or you may say push-pull waves. They are the longitudinal waves. Okay. Longitudinal means the compression and rarefaction type of waves. The motion of the particle is parallel to the direction of the propagation of these waves. Their velocity is 8 to 13 kilometer per second. There means they have maximum velocity. Why their velocity varies? Why they are 8 to 13 kilometer? Not a fixed velocity. It is because of the nature of the material. On all over the globe, there are various types of rocks. There are sedimentary rocks, igneous rocks. Again, in sedimentary rocks, the degree of compaction may differ. The rock type, their type, structure, texture, mineral composition, degree of weathering, their joint pattern, okay, structures in the rock, everything. The properties of the rocks changes, and that is why rock to rock the velocity of P waves or velocity of seismic wave differs. The P wave velocity is maximum velocity 8 to 13 kilometer per second. These are the first waves to reach up to the Earth's surface because they are high velocity. They reach first, and they are the first to be recorded in any seismological observatory or any seismic station. And these P waves are capable of traveling through solids, liquids, as well as gases because they are longitudinal waves. Normally, longitudinal waves can travel through any material. Of course, they require material to travel. They are not just like light waves. They are not electromagnetic waves. Yes? If these seismic waves need material, of course, materials means rock masses. And they are capable to travel through solids, liquids means lavas, magmas, not lavas, I say magma, as well as gaseous material. This is the nature. In this particular figure, you can guess about the nature of the P waves. There are compression, rarefaction type of waves here that is shown in this particular figure. Then second type of wave is S waves. S waves, they are also called as the shear waves or the secondary waves. They are transverse in nature, and that is why they are transverse waves. So S waves are transverse waves. The motion of the particle is perpendicular to the direction of the propagation of the waves. They are relatively slower. Their velocity is normally 5 to 7 kilometer per second. Again, depending on the rock type, their velocity varies. And these are the waves, S waves. These are the waves. They are always recorded after P waves in the seismic station. So the first arrival is of P wave. The second arrival is S waves. S waves are recorded after the P waves on the seismogram data. They are always recorded after P waves in seismic station. They are transverse like light waves. And they are capable of traveling only through solids. They never travel through the liquids. Of course, the property of S waves, the difference in these properties of P wave and S waves has helped us to guess about the interior of the earth, because nobody has seen the interior of the earth. It is not possible to take a borehole up to 6,371 kilometers, that is center of the earth. It is because of the study of the seismic waves from all over the globe, we are able to speculate, we are able to model the interior of the earth. So P waves never travel through liquids. So they are capable of traveling only through solids. And of course, because they are transverse waves, they show little polarization effect. There may be horizontally polarized S waves, you may say SH waves. There may be vertically polarized S waves, you may say uh, SV waves, like that. So there the polarization is normally seen in case of S waves. So this is the nature of S waves. We have seen the nature of P waves as well as the nature of S waves. With this figure, you are easily the nature of the S waves is seen. See this. The motion of the particle is perpendicular to the direction of the propagation, and the waves are propagated to the rock masses. Imagine that this may be some rock mass, this may be a granitic terrain, this may be a basaltic terrain, rhyolitic terrain, whatever, or the sandstone terrain. The same with the same this, with the same mechanism, the S wave is propagated with the 5 to 8 kilometers velocity and reach up to the surface. So whenever we experience the earthquake, a very short time we experience the P wave. Again, for a very short time, the S waves are experienced. But the degree of destruction which is more caused are because of L waves. P wave and S waves are not that much culprit as compared to L wave, because L waves stands for very longer duration. They are the L waves. They are long waves, or they are also known as surface waves, because they are developed whenever these they reached up to surface, and there is a long trail of wave which is recorded on the seismogram after the just arrival of P wave, arrival of S wave, and there is a very long trail of L waves. Whenever we say that there was an earthquake at 10 o'clock, it was experienced for 20 seconds, it was experienced for 30 seconds, the earthquake was experienced for 35 seconds, like that when we talk. This maximum time of 25 seconds, 30 seconds, all on that maximum time is of L waves. Baki P waves, S waves is just very for very short time. And the long trail of wave that caused the destruction is L wave. It is the surface wave, long waves or surface waves. These are the slowest among the seismic waves. Their velocity is less as compared to P wave and S wave. Normally 4 to 5 kilometer per second is the velocity. And these are the last to be recorded in the seismic station. But for longer duration, they are being recorded in the seismic station or in the seismograph. There is a long trail of S waves, and they are very complex. The motion of the particle are very complex. L waves are very complex. The normally it is divided into two types: complex and elliptical particle motions. These are typical characteristics of these waves. These L waves capable of traveling through solids as well as liquids, of course, on the surface. The destruction which is during the earthquake, of course, I just discussed. The destruction during the earthquake is caused by these particular waves, and their journey is confined to the surface layers of the earth only. Only surface layer. Normally, see, L waves are surface waves. Whenever the seismic waves change strata, suppose seismic waves coming through the plutonic rocks at very great depth, and from plutonic rocks they enter into the volcanic rocks, or they enter into the sedimentary rocks. So that particular layer in between plutonic rock and the upper sedimentary rocks, again at this particular junction, the L waves are propagated. Of course, not on the surface. These are there at that location also there are surface waves. These L waves are there, but we experience the L wave just after whenever the seismic trail that comes on to the surface, then we experience the surface wave. So for us, the surface waves are limited to the Earth's surface only, and there is no need to discuss about the change in the medium, change in the type of rock. Mm. That is, there is no need to discuss about that particular surface wave which is within the crust or below the Earth's surface. So, as I told you, L waves are very complex in nature, and they are said to be of two kinds: Rayleigh waves and love waves. See here, these are the Rayleigh waves and love waves. In case of Rayleigh waves, the motion of the particle is in elliptical orbits. Okay, these are the surface waves. The motion of the particle is elliptical orbits, and in case of love waves, you can say they are the horizontally polarized S waves. Such type of destruction is there. Horizontally polarized S waves. If you just tie the rope onto the wall, hmm, and if you shake it horizontally, then the type of waves that goes through that rope, just similar is the nature of these waves. Okay, L waves and Rayleigh waves. Of course, the nature of the L waves is very complex. They are complex, very complex waves, but broadly they can be classified as L waves and Rayleigh waves, like these two here as shown in this particular figure. So they are very destructive, low waves and Larry waves. And there is a long trail of these particular waves that goes through the Earth's surface continuously after any earthquake. And that causes more degree of destruction. And whatever the intensity of the earthquake which we come across on the surface because of the degree of destruction, that intensity of the earthquake is again related with this particular Rayleigh waves and love waves, that is the surface waves of the earthquake. See, with this, imagine that these are the rock materials, and you can see how the nature of the love waves, where the motion of the particle is elliptical orbit, and in case of Rayleigh waves, it is the uh, horizontally polarized S waves like that. That can be imagined, that can be visualized through these two particular figures, Rayleigh waves and love waves. This particular figure I am trying to show you is because, see, the interior of the earth, see, nobody can, as I told you, we cannot take any sample of the interior of the earth, rock sample. We cannot take a borehole up to that particular depth, up to the center of the earth. But by recording the different earthquakes at different location on the earth crust, we can interpret this particular seismic data to understand the interior of the earth. Here, this is the earth crust. The depth of the earth crust is 35 to 50 kilometers, as I told you. Below the earth crust, there is a mantle up to the depth of 2,900 kilometer. Okay, from 2,900 kilometer up to the core of the earth, this material where S waves cannot pass through this material. So you can say that this may be viscous or some liquid material may be there. So from that, then there is a core of the earth, then inner core and outer core, then the transition 500-kilometer transition zone. That everything can be predicted with the help of the seismogram data. So just to know that the how the interior of the earth is predicted and how seismogram data is very useful to model the interior of the earth. Just I am showing you these particular figures. See, this is the data which is generated through the long study of different seismograms, seismological observations. This is the earth crust. The minimum crustal thickness is say 8 kilometers in Pacific and 80 kilometers in Himalayan region. Below that, there is a layer known as asthenosphere. A viscous-like layer is there, and over this asthenosphere, the continents are, you may say literally, the continents are floating over this asthenosphere. Below that, up to the depth of 2,900 kilometers, is the mantle. Asthenosphere is a part of upper mantle. Then from 2900 to 500, 5000 kilometer, 5100 kilometer is outer core, and below that there is an inner core. Again, in outer and inner core, there is a 500 kilometer transition zone. So this is the Morovicic discontinuity, this Gutenberg discontinuity at the depth of 2,900 kilometers. All this interior of the earth, these speculations, they are made from the seismic studies only. That I want to just tell at this particular moment. Now let us discuss regarding uh, the interior of the earth. Oh, sorry, intensity of the earth. Intensity in Marathi we say tivrata. Intensity it refers to the degree of destruction which is caused. More the degree of destruction, more is the intensity. If there is no destruction, very less destruction, intensities are low. Okay. So of course intensity is empirical. Why empirical? I will discuss this point. Intensity is the measure of severity of the shaking of the ground and its attendant damage. That is the intensity, measure of severity of the shaking of the ground and the damage that is caused because of the shaking, because of the earthquake, because of the continuous tail of L waves. Again, at the end, I want to say that intensity is empirical here. Why empirical? To some extent, because degree of destruction or degree of damage depends on many factors. What are these factors? See here. Degree of destruction. Number one, degree of destruction depends from distance from epicenter. You know, epicenter is the point vertically above the focus, point on the ground vertically above the focus of the earthquake. The intensity of the earthquakes, ideally, it should be maximum, and it is maximum at the epicenter of the earthquake. As you go away from epicenter, intensity of the earthquake decreases. Naturally, as you go away, the energies associated with the seismic waves, they decrease, and it is because of that the intensity decreases. So distance from epicenter is very important. In case of Koyna earthquake, the degree of destruction is more in Koyna Nagar. As you come to Patan, it is little less. As you come to Karad, still less. If you go to Solapur, no degree of destruction. If you go to Visakhapatnam, earthquake may not be feeble even. Okay, it may not be felt. So, see, intensity of the earthquake varies place to place. There are two terms, magnitude and intensity. I will come to magnitude. Magnitude for a particular earthquake, the earthquake that has happened on 1st January at 10 o'clock morning, the magnitude is same. Magnitude never changes from place to place. So many times in newspapers, people may read like this, but it is incorrect. Magnitude for every event is fixed, but the intensity differs place to place. As you go away from epicenter, intensity decreases. Then, second is compactness of the underlying ground. That is also the important factor for the degree of destruction. If you construct a house on a strong, compact, massive, intact rock mass is there in the founding, then degree of destruction is very less. Otherwise, if there is no founding, if there is no hard rock up to the depth of 100 meters, and you are constructing your house in the loose soils, then naturally the seismic waves are amplified through the soils and degree of destruction is much more if the compactness is less. So compactness of the underlying ground is very, very important. Okay. Compactness in terms of the rock type, its structure, its texture, its mineral composition, its degree of weathering, its joint pattern, then other structural features like differently we say the laminations in the rock. Uh, These are various factors which are related with the petrology. So petrological aspects are very important. That is the compactness, which govern the compactness of the underlying founding conditions of the structure. So that also is important. It degree of destruction depends on that thing. Number three, type of construction. Any construction with the old fashioned old masonry structure is there, where you have used soil or clay, there the degree of destruction is definitely more. If you construct the house with that, if the concrete is used, reinforced concrete is used, naturally the type of construction, if the construction is strong enough, degree of destruction is less. RCC constructions are very strong, especially in the villages. If you go villages around Killari, wherever there are RCC constructions, they survived. And the old masonry constructions, they collapsed. That too, their north-south wall is standing. Sorry, north-south wall is collapsed. East-west walls are standing. Like that destruction was there in case of Koyna, Killari, all this earthquake. Even in Bhuj. In Bhuj, twisting forces were also there up to some extent. Of course, type of construction is very important. Then the fourth is magnitude of the earthquake. See, magnitude, more the magnitude, more the degree of destruction. It is certain. But in case of magnitude, the depth of focus also along with magnitude plays very important role. That is the sixth point. If the magnitude of earthquake is 4 and the depth of focus is 300 kilometers, definitely the felt area is maximum, no doubt. There will be a very large felt area, but the degree of destruction will be less. Okay, and the intensities which are experienced on the surface, they will be less because of very deep focus. The depth of focus is very high because depth of focus is very high. Sorry. Am I audible? Are you able to see the slide?
Yes, sir.
Thank you. So, magnitude of the earthquake, along with magnitude, depth of focus is very important. If the magnitude just 3 or 3.2 and the depth of focus is just 6 kilometers, then felt area may be less, but the intensities are very high. Degree of destruction may be very high. Okay. Again, the degree of destruction depend on duration of the earthquake. That I talked about the trail of the L waves. Yes, if the magnitude is 3 or 4, but the duration of the L wave, the depth of focus is low, and the duration is very long, naturally the degree of destruction may be more. So duration of the earthquake or the duration of the L wave especially is very important. Then depth of focus. More the depth of focus, highest is the felt area, but less is the degree of destruction. If the deep focus earthquake is there, the depth of focus is below 300 to 700 kilometer, then that earthquake is felt globally. All over the globe, the seismicity is experienced. It is recorded by all the seismographs, but the intensities are very low. In case of Koyna earthquake, if the depth of focus is 9 kilometers or 35 kilometers, then it is experienced in this particular 50-kilometer pocket, but the intensities are considerable because earthquake is shallow focus earthquake. So these are the factors which decide the degree of destruction caused by the earthquake. Okay, and that is why this is the reason by the modified Mercalli scale of the earthquake, scale is imperial. This is the modified Mercalli scale, which is intensities. They are divided into 12 divisions. Of course, the relevant from the civil engineering point of view, they are divided into 12 because it takes into account the factor of acceleration produced in the millimeter per second square. The peak ground acceleration that normally you consider while designing the quake resistant structure, these peak ground accelerations are considered, and depending on the peak ground accelerations, the modified Mercalli scale is designed and into 12 intensities. Of course, intensity can be better appreciated from the effects produced on buildings, ground, people, but it is a matter of discussion. But we find out this intensity based on the seismogram data normally, and from that you find out the peak ground accelerations at certain location, and from that decide the scale of the earthquake. This is the modified Mercalli scale of the earthquake. That is 1 to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the intensities on this side, left hand side. These are intensities are named. Whenever there is intensity 1, it is known as instrumental. It is only recorded by instruments. The peak ground acceleration is less than 10. Okay. Then intensity 2 is feeble, then slight, moderate, rather strong, strong. Intensity 7 is very strong. Intensity A is destructive. Intensity 12 is catastrophic. Literally, the ground rises into the air and falls down. There are the waves are seen in the rock masses. Actually, the catastrophic type of earthquake is there. Okay. So this is the modified Mercalli scale. See how these particular intensities are related with the effects that can be seen in this particular table. Intensity 1 instrumental means recorded by instruments only. Intensity 2 is feeble. Intensity 5 is rather strong. You can say many persons awakened, dishes broken, plaster cracked, trace and these poles are disturbed. Like that, you can associate with these figures of intensity with the degree of destruction that is observed. Okay, observed by people in the felt area. You can decide the intensity. So this scale is normally used, okay, and applied in earthquake engineering. That is scale, modified Mercalli scale of the intensities because it is related with the peak ground accelerations. Now let us see how to locate the epicenter of the earthquake. If there is an earthquake, how to find its epicenter? It can be located easily for any earthquake taking advantage of the time lag noticed between P and S waves. Imagine that two people started running from one place, X person and Y person. The velocity of X is say 10 kilometer per second. Velocity of Y is 1000 kilometer per second. They started running from same point. Okay. And they ran for certain distance. Naturally, why? Because its velocity is more. He will arrive first and then X after. But the time lag, more the time lag between the arrival time of X and arrival time of Y, more the time, more this time lag, more is the distance of their starting point. The same principle is there. The P wave velocity is different, S wave velocity is different. The time difference in the arrival time of P wave and arrival time of S waves, it helps us to decide the distance of your epicenter, not direction, but the distance of epicenter from your seismograph that is used. The time lag between the arrival time of P and S waves, it increases gradually within the distance from the epicenter. Okay, and this factor gives a measure of the distance between epicenter and seismic station. How this you can see with the help of these figures. See, this is the seismograph A and B. They are the seismograph stations. Are you able to see the figure? Are you
Yes,
able
sir.
to see the
Yes,
yeah.
yes, sir.
See, this is on the surface. This is a seismograph A and seismograph B. And this is the focus of the earthquake. At particular event, this particular is the focus. Okay. And the seismograph, which is a seismogram, which is recorded at A, is like this here. PS. Every seismogram, SV seismograph is associated with the atomic clock. Very accurate times are also recorded along with this particular seismogram data. The seismic waves are recorded and time is also recorded, and that too with the help of atomic clock. High precision instruments are there. So whenever here it is recorded, arrival time of P is recorded and arrival time of S is recorded. The first from this focus, P wave will come first, it's recorded here. S wave comes later, it is recorded here. So this time lag between arrival time of P wave and arrival time of S wave is less in this case because focus is very near or epicenter is very near from this location. In case of B, seismic station is at B, it is far away from focus. Then naturally the arrival time of P wave and arrival time of S wave, this time lag in between these two is more. या दोनातला the time lag between these two increases gradually as this particular distance increases. Okay, arrival time of P and S waves, and this is plotted on the standard curves like this. This is one more figure I'm showing you to understand the actual seismogram data is there. So arrival time of P wave and arrival time of S wave. The P and S wave, this time lag is plotted onto the standard curves. Again, third example is this. Here, P1, P2, P3, that is north-south component, east-west component, vertical components are separately recorded, and the data is more accurately taken, and it is arrival time of P wave, arrival time of S waves that you can see with the blue and these red lines, and this particular time lag is plotted on the standard curves. Depending on the various types of rock masses, such type of standard curves are available in the seismological observatories, seismic stations. Here we see on the x-axis you have distance from focus or distance from epicenter. Likewise, you may design. Okay, and distance from epicenter, and it is the travel time in minutes or in seconds, whatever. Different for different types of rocks at different seismological stations. This type of standard these are available. Standard curves are available. This curve is for P wave, and this is for S waves. You can plot arrival time of P wave and arrival time of S waves onto the standard curves, which are developed for different areas. Okay, and from this you can find out the distance of epicenter. In this case here, you can find out the distance of epicenter to be from this time lag, distance of epicenter, this time difference, distance of epicenter from your seismograph, say somewhere it may be 9,000 kilometers. With this particular exercise, you come to know the distance of epicenter or distance of focus from your seismological observatory, seismic station, but you may not know the direction. For finding out the direction, at least minimum 3 seismic stations, they should not be collinear. Okay, minimum 3 seismic stations are required. So with the help of that, just wait a little. It's not being changed. Okay. नाही आलं की थोडासा केवढा वेळ लागतो डेटा साईज जास्त असेल इमेजचा वेळ लागतो so at least 3 different seismographs are required. Am I audible, please?
Sir,
Yes. So seismogram A, seismogram B, seismogram C. Here you can see this arrival time of P wave at this A, B, and C. So you will get three distances from 3 different seismic stations, and you can plot them here on the map. In the GIS environment, you may map the distance of epicenter. You suppose this distance is 2000 kilometers, then you take a radius of 2000 kilometers, and in the GIS on the map you draw the circle having radius of 2000 kilometers. If another is 4000 kilometers or 8000 kilometers, you draw the circle having the same radius. And for third seismograph, the third distance, you can take the distance of epicenter as radius and draw the third circle. So wherever you get the intersect of these 3 circles, that is the epicenter of the earthquakes. This is a very common practice of finding the epicenter of the earthquake with the help of this, not focus, but epicenter of the earthquakes. And for the depth of focus, finding out the depth of focus below the epicenter, there is another exercise that I will tell you in short. See, by collinear, the seismographs or the seismological observatories, this should not be collinear. If they are collinear, then you will not find the correct epicenter. There will be a confusion whether this epicenter is near Mexico or it is in Canada. There will be the confusion. So, of course, these Pre-seismic station should not be collinear. That is the only thing which is required. Now, how to determine determining the depth of focus of an earthquake below the epicenter? So, according to Oldham, the depth of focus can be estimated by comparing the intensities at epicenter and at another station. Intensities, of course, intensities found out with the help of seismogram. Intensities can be calculated with the help of peak ground acceleration, with the help of the amplitude of waves, with the help of duration of waves, wavelength. All wave parameters you may consider and find out the intensities. That is possible. And that intensities are considered for finding the depth of focus. See this particular figure. Imagine that this is a cross section of any ground. E at point E is the epicenter. F is the focus. Focus is a point below the epicenter from where the seismic waves are originated. Say depth of focus is H. Okay, and this is the G is geophone. Geophone means seismogram. It is a seismograph. Here the seismic station is there, seismological observatory where there is a seismograph. Okay, so that G is used notation. The intensity at epicenter is M. The intensity which is calculated at epicenter, it is M, and the intensity at your seismic station is N. Okay, the D is distance of epicenter from seismic station. Now see which parameters are known. Earlier two exercise, if you study, they have given us the distance E and G. The distance between the epicenter and seismological station is known. That is D is known. You have also calculated the. Yeah, we have to calculate this particular H. How to calculate? By inverse square law, M upon N here. N upon M. N upon M is incorrect. It should be M upon N. It is wrongly written, excuse me. M upon N is equal to H square upon R square. Okay. That is the inverse square law. M upon N is equal to H square upon R square, which gives you H square upon R square is sin square theta. So from this exercise, you can find out theta. Theta is equal to sine inverse of H square upon R square. Okay, M upon N is known. Therefore, theta is equal to sine inverse of M upon N. From that, you can find out the theta with the help of these intensities, intensity M and intensity N. Theta is equal to sine inverse of root M upon N. Once you know theta, you can easily calculate H. That is the depth of focus. H is equal to D is known, D tan theta. This equation will give you the depth of focus below the epicenter. So this is a common practice by which the depth of focus can be calculated below epicenter. So we have seen two methods: how to locate the epicenter of the earthquake, how to find out the depth of focus below the earthquake. Now let us enter. Now let us enter into the little plate tectonics and earthquake distribution. And at the end, we will come to the Koyna earthquake now. Plate tectonics and earthquake distribution. Earthquakes occur at the boundaries of the crustal plates. Most of the earthquakes, 90% of the earthquakes, they are occurring at the boundaries of the crustal plate. They are plate boundary earthquakes. Okay, whenever the plates interact with one another, there are different types of plate boundaries. There are convergent plate bounding, divergent plate bounding, transform fault boundaries are there. And they occur randomly along certain narrow continuous belts. Encircle enclose large regions known as in the plates. So the intra-plate earthquakes are there. So these particular areas where the earthquake occurs frequently, they are known as the seismic belts. So which are the very common seismic belts? Seismic belts are those places where earthquakes occur frequently. And the shield areas are those places where earthquakes are very, very rare. Yeah. Normally, the tectonically formed mountains like Himalayan mountains or the orogenic mountains or epirogenic mountains areas, mountainous regions. Then at the steep coasts, these are the very common places for the earthquake. How much time? 12:30 आहे का? 1 पर्यंत नाही. Okay. So time is very less. I will go a little fast, please. So 50% of the earthquakes have occurred along mountain ranges and 40% earthquakes along steep coast. So these are the seismic belts. Very common seismic belts are Circum-Pacific Belt, Mediterranean Belt, Alpine Himalayan Belt, Rift Valley region, in the Central Africa, Mid-Atlantic regions. These are the common seismic belts. I will not go in detail now at this moment. Time is very less. Just I will go fast. So this is how the earth crust is divided into more or less 20 plates, and 7 plates are very important, like North American plate, South African plate, Australian plate, Antarctic plates, etc. And if you see the earthquakes, the focus of the earthquake, this is the map showing focus of the earthquakes, which are concentrated along the plate boundaries. Seismic movement, I will skip because of the time. I'll not discuss more about seismic movement, earthquake magnitude. Richter magnitude is very common, that we know. That is, Richter magnitude is defined here. Richter magnitude is local magnitude as the same logarithm to the base 10 of the maximum trace amplitude in micrometers recorded on the Wood-Anderson seismometer is a common Richter magnitude. Of course, it is always the most appropriate scale overall, but for a civil engineer, different types of magnitudes are required for designing the structures. There are surface wave magnitude, coda magnitude, body wave magnitudes are there. They are studied in the earthquake engineering. Some other instrumental magnitude like this, duration magnitude, coda magnitudes, they are used, moment magnitudes. Moment magnitude gives us the total energy released, except to calculating exactly the total energy that is released during the earthquake. And with the help of these magnitudes, such type of nomograms are available in the seismological observatory. From that, you can easily calculate the magnitude of the earthquake. I will just skip this particular part. Okay, the total energy released during the earthquake, how many energy for how much magnitudes, that I will go further. As far as prediction of earthquake is concerned, only one earthquake was predicted in China. That is the only example. Otherwise, earthquake is the unpredictable event. I will not much discuss, but earthquake is still unpredictable event, and you have to go in for some techniques like base isolation technique or any other civilian techniques by which you can construct the quake resistant structures. Entering into Koyna, like 10 minutes, 10 to 15 minutes. Uh, this is the Koyna region. This is the old graph which is by Professor Dr. Guha. This Koyna earthquake and the intensities are shown. It is of 1968 or 70s figure is there. So just from this we know that this alignment of Koyna river up to Koyna Nagar is north south alignment is there, and there is hypocentral line from Koyna Nagar to Varna here. This is the Indian seismic zone map. So this Koyna region is a very smallish pocket, having now zone 4, in which the seismicity is very common, and every year the frequency of the earthquake and intensities of the earthquake is considerable. That is why this Koyna earthquake is taken into consideration by NGRI. That is, there is one institute here in Karad, BGRL. They have planned to take the deep boreholes, and they are going to insert certain sensors in this borehole. They are trying to make a solution for the prediction of the earthquake. But yet, till date, the earthquake is unpredictable. If you consider the seismicity of Maharashtra, if you see the morphology of the Maharashtra, we have high level basaltic plateau, structural hills, valleys, the southern scarp of Satpura fringing Tapi Purna river, structural and denotational peneplains in eastern part of the state, because our rivers like this Krishna, Godavari, these rivers are eroding the bedrock for last 53 million years. So very huge peneplains have developed in the eastern side and the western side. In Konkan region, we have the scarps of Sahyadri or the Western Ghats. So such type of rugged terrain we see in Maharashtra, in Koyna region especially. Then this is the morphological map of Maharashtra that you can see. Will not go in detail now. The seismicity of Maharashtra is related to major 9 lineaments. See, not with any reservoir, please. I am against the thinking that reservoir is induced seismicity or reservoir triggered seismicity. So, especially the people who have learned structural dynamics and fluid mechanics or hydrology, these people at least, I think that they will never believe the any dam or its reservoir is responsible for seismicity is incorrect. uh, these 9 lineaments, these Tapi lineament, triple lineament, one lineament is a line-like structure that is seen in the satellite imagery. Just I will show you what is lineament so that you will get the idea. Are you able to see this? Are you able to see the satellite imagery I am showing? You see these line-like structures in western side. You see these are the lineaments. Okay, whereas this village is patterned, and along pattern, many scientists have shown some lineament, but actually they are not there. There are no faults. This entire area is structurally undisturbed. Koyna reservoir, Koyna water is very compact, intact. Even if you take a borehole alongside the Koyna reservoir, you will never get a water. In excavations for the Koyna project, the groundwater problem never exists. So Koyna water is not percolating. So groundwater water percolating at the depth of 20 kilometer, if people are saying, and that is responsible for the earthquake, it is incorrect. That okay. So the reason is these lineaments, and these lineaments, 9 major lineaments, they indicate the structural disturbance in the Archean rocks below the Deccan Tract, where the stasis are being accumulated and released in the form of earthquake. Seismicity of Maharashtra is totally related to this 9 lineament. Just let me go further. Okay. These are the lineaments. Of course, there are gravity loads which are observed at Koyna. We are having very less time, so I've been advised to conclude the lecture. Just for concluding, I will go further. Just wait. So, in fact, excuse me for I could not manage the time. See, the Koyna Dam is a so keeping the trust that in Koyna Dam is a classic case of reservoir-induced seismicity, but the senior project officials initially denied this particular link of reservoir with the earthquakes. It is because I will not now discuss these particular things. First, just let me say what is reservoir-induced seismicity. See, it is the occurrence of earthquakes triggered by the construction and filling the large reservoirs caused by the immense weight of the water and increased fluid pressure, altering stresses on pre-existing faults. So, seismicity which is related with the reservoir, seismicity which is developed because of reservoir, it is known as reservoir-induced seismicity or reservoir-triggered seismicities. But Koyna Reservoir is not a reservoir triggered seismicity. It is a typical tectonic type of intraplate seismicity which is related with the structures in the Precambrian rocks or structures in the older rocks below the Deccan traps. That is what I believe. I would have discussed more, but we do not have time because this is 48,000 square kilometer Deccan Trap region is experiencing seismicity, how much energy is released, and what is the shape and size of Koyna reservoir that you please compare. So it is no way related with Koyna water, reservoir water. I will show you these points and conclude. Why? These are the key points on the denial end of the scientific view. Why Koyna reservoir is not related with the earthquake. It is not reservoir induced seismicity, or it is reservoir, or neither it is reservoir triggered seismicity. Because height of this Koyna dam just 80 meter thick column, that is to some square, see 770 square kilometer. It is not able to create the stresses which may trigger the seismicity. And it is not possible that Koyna reservoir water is percolating up to the depth of 20 meters and causing the pressures to trigger the Koyna seismicity. How can it be? So thank you very much, and kindly excuse me that I could not discuss in depth regarding the reservoir induced and reservoir triggered seismicity of Koyna reservoir. But at the end, just I want to say that I personally, especially uh, the engineering community, civil engineers, they don't believe the fact that there is a reservoir induced seismicity or reservoir triggered seismicity exists in case of Koyna River. So thank you so much for your patience listening and giving me the chance to participate in this particular FDP. Thank you so much once again, and thanks to the organizers.
Thank you, sir. Participant, if anyone has any questions or doubt regarding today's session, please unmute yourself and ask. Okay. Respected.
Thank you.
Hello. If anyone has any doubts, comments.
Yes, excuse me, sir.
Yes,
Yes.
please.
Sir, you have already shown the various equipments we can measure the earthquake. So, how the digital media nowadays is involved, like drone or anything, to have the ease in measuring this earthquake or the predictability?
No, digital media is not yet successful in measuring the predictability. Earthquake is yet not predictable. The only thing that we are getting now the lidar data or high resolution satellite data. This high resolution satellite data helps us to find out the lineaments or the structural disturbances in the rock masses. And with the help of the structural disturbances, you can find out the locations which may be prone to the earthquake. That is possible. But you cannot predict.
Okay, okay, sir.
Yes, you can measure the lineaments. Just I had shown you the this particular satellite imagery. One more image I will show you, that is the list data or the TM data. Let the image is being opened. By the time you can see this particular image, see, lineament is a line-like structure. This is a Koyna dam, and the west to the Koyna dam. Yes, this is open. I am showing you the IRS 1D satellite list 3 data here, and over to on this data, if you see on the west side of the Koyna dam, you can see can you see these line-like structures? Say this line, this one is lineament, this is
Yes.
lineament, this is lineament. These are all structural lineaments. They are in Konkan. They are very near to sea, Samudra.
Okay,
Okay.
okay.
So this area would have been more prone to earthquake. We are experiencing earthquake in this particular region. So
Okay.
the severe lineaments are not mapped alongside of Koyna or eastern side. So there is no structural disturbance in Koyna region that is responsible for the earthquake. It is
Okay,
below the
okay.
Deccan traps. So this is how the digital media is useful in
Okay, sir. Thank you
with
very much.
respect to satellite imageries. Thank you so much. Yes, please.
Sir, there is a one question. What are the applications of AI in earthquake?
What are the application of AI? Actually, I have not been exposed to AI so much, but
Okay.
I think AI is just a tool for information.
Yes. Oh, okay, sir. Yes.
But in case of earthquake, uh, I don't see any. I don't.
Okay.
In fact, I don't know AI.
Oh, okay, okay, sir.
Can I have one question, please, sir?
Yes, please.
Yes, yes, please.
Sir, how you could say that now recent developments are affecting the rock masses in the northern Himalayas and the lower Himalayas?
Huh.
Construction over there, we are using extensive TBM constructing. So how that would affect the Himalayan ranges in terms of earthquake and development of or widening of the fault zones?
Yeah, in Himalayan region, yes, because Himalayan area is young area and very high reliefs are there, so continuous erosion is there, and because of this severe erosion by the antecedent drainages, these all Himalayan rivers, Indus, Satluj, Kali, Tista, Ganga, Ghagra, Brahmaputra, all these Himalayan regions are the Himalayan rivers are the antecedent drainages, and they continually erode the bedrocks. Because of erosion, there is a weight imbalance which is responsible for the isostatic adjustments. And during these isostatic adjustments, there is a folding and faulting. These processes are still being continued in the Himalayan region. Okay, and they are at very shallow depths. So there are shallow focus earthquakes are very common in the Himalayan region. They are going on, and that is why this region is highly prone to earthquake.
Thank you, sir.
Yes.
Okay. Respected Professor Deshpande, sir,
Yes,
respected
please.
coordinators, faculty members, and dear participants, on the behalf of organizing committee on this Atal Faculty Development Program, I express my sincere gratitude to Professor P.K. Deshpande for delivering such an enlightening, informative, and provoking session. Sir, your vast experience in geology, remote sensing, GIS, and especially earthquake related studies was clearly reflected in today's lecture. The way you explained complex concepts such as magnitude, intensity, seismic waves, fault mechanisms, seismograph in detail, using real life examples like Koyna Dam, made topic clearly relatable. The live examples not only enhanced our understanding but also help us to visualize how theoretical concepts are applied in real world scenarios. We truly appreciate your willingness to share your knowledge, research experience, and academic journey with us despite your busy schedule. Sessions like this greatly contribute to success of Atal FDP and faculty members upgrade their skills in line with current research and industry needs. Once again, on the behalf of entire team, I thank you, sir, for your time, expertise, and inspiring presence. We look forward to more such an interaction with you in future. Thank you very much, sir.
Thank you. Thank you so much.
Yes. Now I declare as the session is over. Next session will start at 2 p.m. sharp.
Thank you.
Thank you, sir.